So today we'll be looking at probabilistic models. First, the announcement. So there will be a recitation tonight on probability, if that's something you want to brush up on. Note the room change. It'll be in Annenberg 121, which is just down the hall. Going back to sort of the topic overview that we've been looking at on and off during this course, we started with supervised learning, right? And then we talked a bit about unsupervised learning, and then within these sort of two sort of tent poles, we looked at various model classes, including linear models and nonlinear models, questions of overfitting, bias variance trade-off, different choices of loss functions, learning algorithms, optimization, and now in the last part of the course, we're going to look at probabilistic modeling. And probabilistic modeling can work in both the supervised and the unsupervised setting. In some sense, probabilistic model is fairly agnostic to which setting you're in, and I'll sort of make that point more clear as this lecture proceeds. Right. So today we'll look at sort of introduction to probabilistic models. We'll go over in detail the simplest probabilistic model that people use in practice, which is Naivebayes. We'll talk about methods for learning, estimations, and how to sample from it. We'll do a little brief survey of more advanced probabilistic models, and then on Thursday we'll talk about hidden Markov models, which is a probabilistic model over sequences, which is probably the most popular sequence modeling technique in use today. So, in a probabilistic model, also known as a generative model, the goal of the model is to model the joint distribution of x and y, right? And so, from there we can make a prediction of y given x using an application of what's called Bayes rule. How many of you have heard of Bayes rule before? Okay, so about 2/3 or 3/4 of the class. Okay, so normally when we do something like this, right, we do it by let's say logistic regression. We train a p of y given x using logistic regression. Here, we actually don't learn p of y given x directly. We learn p of x comma y, right? And what that allows us to do is that allows us to compute p of y given x by applying Bayes rule, which is simply first you rewrite this using the laws of conditional probability, which is p of x comma y divided by p of x, and then you can rewrite this part as p of x given y given p of y. And so if you have a joint distribution, these two terms, this ratio and this term are equivalent. And so if we learn these terms, then we can make a prediction of p y given x by applying this rule. And that's a lot of the game that we'll play when we talk about generative models. Right. One of the nice things about generative models is that because you're modeling the whole distribution, you can compute any kind of marginal distribution that you like. So for example, you can compute p of y, that's it, right? Which is simply, by the laws of total probability, the sum of overall possible x, p of y comma x. Similarly, we can compute p of x, right, which is the sum of overall possible y, p of y comma x. These are things that we can do. When x and y are continuous, of course, we would have to replace the summation with an integral, but otherwise, conceptually, things are sort of stay the same. Any questions on that? And we won't be dealing with the case where x and y are continuous and we have to use an integral. That leads to a number of computational challenges that are beyond the scope of this class. Although in practice, this is, of course, an area that is of active research in the machine learning community. For simplicity, we'll just look at the cases where y and x are discrete, often binary. So each x and y will just take on a single binary value of 0 or 1, just to keep things simple. But conceptually, everything sort of extends, at least at a conceptual level, in a very straightforward way. Here's an example. So here, just you have a little training set here, right? So we have one feature x, so a one-dimensional feature. It's binary, right? And a binary y, right? And here is sort of the model that we've learned. So we've learned a p of x comma y. So here we can think of this as our model, right? The parameters of our model. It's a little bit different than a linear model class, but there's a relationship. And so given this model, right, we can now, first of all, we observe that it's an actual probability distribution, so it sums to 1. That's a requirement of it being a probability distribution. And now we can, ask a question like, okay, what is P of x equals homework, right? And we can just compute that by taking the by marginalizing out the y variable. So we have this P of x comma y. We sum over all possible y with the same x, where x equals homework, and sum over all possible y. And we get the answer is 0.5, right? So this is also known as marginalizing out the y. Okay, we can ask the question of what is the probability of y equals span given x equals health, right? And so again, we can apply this rule, right? So this rule says P of y given x is equal to P of y x comma y divided by P of x. So P of x we already know how to compute. We just set x equal to help and sum over all possible y. And then x comma y is span, help comma span, right? And so that gives us an answer of 0.6. Right, this is the same kind of prediction you would make. This is the same kind of prediction you would make with logistic regression, right? We're just computing it in a different way by starting with the joint distribution. Okay, here's something that you can't do with logistic regression. We're going to predict P of x given y, right? In logistic regression, because of the way it was trained, you can only predict P of y given x. But if you model the joint distribution, you could even predict P of x given y, right? And it's in this particular case, in this particular example, the model actually does not even care which one's x and which one's y, which one's the target, which one's the input feature, right? It's modeling the joint distribution in a perfectly symmetric way, right? So either one can be the target, either one can be the input feature, right? And so then you could compute a computation like this using the same trick. Now we just treat y as the input variable and x as the thing to predict, the target, and we just apply the same trick, where now we marginalize out the act. We now marginalize out the x when we compute P of y, right? And so you get an answer that looks like this. Right. And this is something that you could not do with logistic regression. And of course, things can get a lot more complicated. This is a very simple example. Right. So just in this simple example, if our goal is to learn this P of x comma y given training data, right? What is the objective function? Right? It's going to be maximum likelihood. In all the probabilistic models that we look at in class, the training objectives is some form of maximum likelihood. And so the raw form, the native form, is you have a training set S, which is a bunch of XY pairs, right? Sampled independently from the true distribution that we're trying to learn. So there's some true P of x comma y, right? There's a true P of x comma y. We get samples from it, and then we want to sort of fit the parameters of our model, which are these 6 numbers, to maximize the probability of observing this training set, right? And so it looks like this. Again, oftentimes it's more convenient to minimize the negative log likelihood, the log loss, right? And so this is what the form of the model looks like, right? And you will see an example, of this in practice. But for this type of model, it basically solving this reduces the frequency counts, right? So, what is the frequency of observing this XY pair in the data set? Yeah. And we'll see a derivation later on for the Naivebayes model class. But that's basically how it works for this simple case. And the number of parameters here is 6. Yes.
Can you explain intuitively what does this goal function mean?
The what function?
Goal function. The goal is goal in the learning. I mean, just multiplying the probabilities doesn't make sense. Why is it?
Oh, why we're multiplying here?
Yes. And
because we're assuming every data point is sampled independently. So therefore they're independent of each other. Therefore we can multiply the probabilities together.
Yes, but you wanted to increase the, I mean, initially what was the goal function?
The goal?
Yeah, what was the learning objective?
The learning objective is to find the parameterizations of our probabilistic model that maximizes the likelihood of the training data, of observing the training data. If you think about, yes.
So we're trying to figure out, we're trying to learn the P's such that the observed X I's and Y I's are, probability of seeing them together are maximized?
That's right. That's right. I mean, one could do more, one could regularize, right? One can do all those things, like regularization and things like that, but I'm not dealing with that here. Yeah, so you could overfit to the training data in this form. Right, so we don't actually learn a generalizable distribution. We just learn the particulars of the samples that we collected. We'll talk about issues with regularization overfitting later, but this is sort of the unregularized learning objective, if you will. If you think about this in terms of unsupervised learning, right? Suppose we're just trying to somehow have a parameterization of our model that summarizes the data, right? That can reconstruct the data. Right? If we were to draw samples from this model, right? We have this model, we can actually draw samples from it. With samples that we draw from this model, the simulated sampling, look like the data that we collected. Right? And this is one metric. This is one metric to quantify how good that looks like. Yes?
Where do you encode the constraint they have to sum to 1?
Where do I encode the constraints?
Is that, like, if you scale everything linearly?
Oh yeah. It's implicit. The fact that it's a probability here is it's implicit that it sums to 1. Yeah. If we look at some of the, I didn't actually show you how to solve this. So when you actually write down the mathematical optimization problem, there will be an explicit sum to 1 there. Here I kept it as just probability. Yeah. Was there another question? Okay. Yes.
I'm still not clear, like, how does X and Y describe the model?
How does X and Y describe the model? X and Y does not describe the model. These 6 parameters describe our model. These 6 parameters. So I suppose in this particular case, there's sort of a one-to-one correspondence because it's a very sort of explicit model that where you have a single parameter per XY pair. And there's something I'll touch on later in the lecture. But these 6 parameters describe the model. And we want to find a setting of these parameters that maximizes the likelihood of observing the collected training data.
So it's not like really clear here. So what's the P of X, Y? That's the true possibility, or?
This is the model that we're trying to learn. This model has 6 parameters, which are these 6 numbers. And we're trying to learn these 6 numbers in a way that maximizes this objective.
So isn't that like some close form that the 1 is just equally distributed around all the possibilities?
I'm sorry, what?
Like, for example, in this case, we would have like 6 scenarios. So wouldn't that the P of X, I, Y, all equals 1, 6 would maximize this?
No, because if like this pair, right, if in the training this pair happens 4 times as often as this pair, then that would not be the case.
And how do you express?
What do you mean? How do you express that? If we have a bunch of training data, And in this collection of training data, this pair happens 4 times as frequently as this pair. The maximum likelihood solution would not be to have those be equal probability. The maximum likelihood solution would have this one be 4 times as large as this one. And we'll see a derivation of this later on in the course, where I actually unpack what this probability is, set some constraints, require them to be sum to 1, all that stuff. We'll actually have an explicit mathematical optimization problem written out where you can see that very explicitly. Here, I'm just sort of saying, if we were to solve this at this abstract level, this is the solution.
So P here is the probability that the P of X, xi, yi actually models that will predict the true distribution.
We're trying to model the true distribution. We're trying to find a parameterization of our probabilistic model that as closely matches the true generating distribution as possible, given samples sampled independently from the true generating distribution. Yes?
So you said that there are 6 parameters for this example. Is it always true that there are the number of training examples parameters per P?
The number of examples can be more than 6. You can have 1,000,000 examples.
And then still end up with 6 parameters?
That's right. The number of unique, in this particular example, the number of unique or distinct examples is 6.
Okay.
Yes?
How would this generalize to like the continuous case?
You'd have to make some smoothness assumptions in the continuous case. And then subject to smoothness assumptions, then a point estimate, like if this was like 2 continuous numbers, would then be able to, because you make a smoothness assumption, you can actually let that point estimate diffuse out.
So
Similarly to, if you are modeling something as a mixture of Gaussians with a known covariance, known variance, then receiving point estimates allows you to actually blur out the resulting distribution. Yeah.
okay. And smoothness in this case, like Lipschitzness or like?
Typically, you need to make something stronger than Lipschitzness. For example, if the emission probability is Gaussian, right? So or the emission probability is exponential or whatever. Yeah. You'd have to make a more explicit assumption. It'd have to be an explicit model, I guess. Yeah.
Okay.
Such as Gaussian exponential. I mean, there are more complicated ones as well. Okay, I think some of these questions some of these confusions will become more clear as we run in the lecture. So the interpretation here that I try to convey is that given a specific structure of the model, and this particular model is unstructured, we're learning a single parameter per unique or distinct XY pair, but given a specific model structure, find the parameterization of that model that best explains the data under the maximum likelihood assumption of explanation. And we'll look at something that's more structured in naive Bayes, which is the bulk of this lecture. Right. Here's the training derivation. So here I'm explicitly writing out the probability as in a way that it has to sum to 1, right? And then we're going to solve this optimization problem. We're minimizing negative log likelihood, which looks like this, right? This should be very reminiscent of what logistic regression looks like when you're minimizing log loss for logistic regression. And you compute the gradients, right, with respect to a single parameter in your in the model. You set it. You have this equivalence. And you have this, you set the gradient to 0 and you did the solution. Right? And so if you take this gradient and you set it to 0, you get this as the answer, which is the number of times that this specific XY pair appears in the training data divided by the total number of training examples. Again, this is no regularization. And this is a simple model class where we have one parameter per unique XY pair. But this should give you an idea of how to solve for these types of learning objectives. And this is the type of solutions that we get. They're just counting. So a W is a parameter. So there's 6 W's. Yes?
The bottom sum adds some kind of regularization already, or
No, there's no regularization here. Yeah. So in particular, if some XY pair, one of the 6 XY pairs does not appear in our training data, it will be 0. Right? Which is very extreme. Okay. So let's talk a little about regularization. So one of the simplest ways to regularize in these types of models is to use what's called pseudo counts, right? Because in the unregularized version, you're just basically counting. You're just doing some frequency counting. In the regularized version, people just add pseudo counts. So we had discussed this in a lecture the second week of class, where you could actually, in some cases, establish an equivalence between hallucinating training data, right, and standard forms of regularization. So here I'm just going to jump straight to hallucinating training data, right? In many cases, you could still form an equivalence with some form of regularization, but here I'm just going to jump straight to hallucinating data. So, for example, I can add a probability of 1/6 here, right, for each of those examples. So there's 6 unique parameters, 6 unique data points. So I can put p equals 1/6 here, and I have some lambda to 1, I guess, in this simple example, right? In which case, I will never predict that some entry has 0 probability. But a priori, in the absence of any training data, I would assume that it's a uniform distribution, right? And this is the most common way. One of the most common ways that people do regularization in these types of models is to simply add they call it pseudo counts. It's equivalent to the idea of hallucinating training data that we talked about in the second week of class, yes?
So do you do this for each of the p of x, y that you are training, like each of the parameters?
That's right.
Does it still sum up to 1 then, like the probability?
Yeah, because this is a problem. Because it sums up, yeah,
Okay.
divided by lambda. Right?
Okay.
This sums to 1, right? So therefore, this thing sums to lambda, basically. You're adding a lambda to the numerator, to the denominator.
Okay.
And lambda is the hyperparameter that controls the strength of the regularization. Okay. Okay, so these types of probabilistic models are also often referred to as generative models, right? They model both the x and the y, and therefore they can actually generate complete new data points, right? So, because all the data points from the true distribution is sort of an xy pair, right? So therefore, being able to generate brand new data points, which are basically xy pairs, is part of the power of these generative models. Now, in the unsupervised case, where we just have x, right? In the unsupervised case, we just have x. Then this model is able to just generate new x's, right? If we learn a p generative model that fits an unsupervised data set well, then we can learn to generate new samples. And I'll give you some examples of that at the end of this lecture with some more advanced methods, like generating new images, hallucinating new images from a training set of images. For Mini Project 3, you'll be generating new Shakespearean sonnets from training from a data set of Shakespearean sonnets. Those are unsupervised learning tasks. In the supervised case, it just treats the entire XY pair as a data point, and it wants to have the ability to generate an entire XY pair. In contrast, we spent most of this course on discriminative models, which is sort of what you do for supervised learning, where we don't necessarily want to model the x that well. We only want to model how to predict y conditioned on x, right? Which means, in the case of logistic regression, we're learning this. We're directly learning this guy, right? And so we won't be able to generate new training examples, right? Because that requires being able to generate an x, and none of these discriminative models can generate an x. They can only predict y given x. All right, so what are some benefits of drawbacks, right? Generative models, so in this case, in this very simple example, right, it requires 6 parameters in the example, right? You can sample the whole distribution, so you can hallucinate a new training example. In this case, it doesn't make as much sense because there's only 6 distinct possibilities, but for more complicated models, such as generative models of images, this is quite interesting. You can make predictions via Bayes rule, right, as we saw before. And you can even tolerate missing data, which I'll get into an example of later. On the other hand, in discriminative models, right, their goal is to, typically for the same type of task, if your goal ultimately is to predict y given x, and you don't care about modeling x at all, just only condition on it, then it's typically a simpler model to get the same outcome, or get much more accurate answers. But you cannot generate new examples, and you cannot tolerate missing data, right? If you have a missing value in your x, right? If you didn't measure every feature value, and the one feature entry is just missing, you don't know what it is, then a discriminative model like an SVM or expression, they won't know what to do. The weight vector is learned under the assumption that you observe every feature entry, right? If you were missing one, you wouldn't be able to actually do something reasonable. So the upshot is that if everything is sort of in the idealized setting where the only thing you care about is predicting y given x, you have a supervised training set of x, y pairs where you only care about predicting y, and you don't have any missing values, then the types of supervised models, discriminative supervised models like logistic regression, SVMs, artificial neural nets, decision trees, they will make better predictions if you know for a fact that that's all you want to do with this model. Right? And in fact, for the bulk of machine learning that's used in industry, where each model has a very specific task, right? This is what people do, right? They learn discriminative models like random forests and neural nets, and so on and so forth, right? Generative models, right, require sort of learning much more than what you need to learn, right, in order to make this prediction, right? You have to learn this guy, and then from this guy infer this guy, and there's so many ways that you can learn a miscalibrated model that can make really bad predictions if your goal is to predict y given x, right? And the training objective doesn't even maximize accuracy, right? The training objective isn't to maximize p of y given x. It's to maximize p of x comma y, or p of y comma x, right? So the learning objective is not actually aligned with maximizing p of y given x, which is what the logistic regression learning objective is. So all the stuff that you did for the Kaggle competition, right? If you used the generative model, you probably would have gotten in last place. Yeah. Any questions on that? Okay. So, because generative models are joint models of x comma y, right, or in the unsupervised case just x, right, they fully specify a probability distribution over all the things that define a data point, right, which in the supervised case is x comma y, right, and so you can actually generate new data points, right. So here's just one really simple example, right. So for this model, again, this very simple model here, right, we're just going to have a random variable that's drawn uniformly between 0 and 1. It's called rand in Python. And then if that random number is less than 0.5, then we emit this guy. Otherwise, if the random number is less than the sum of these two, which is 0.25, we omit the second line, and so on and so on. Right, so this is a very simple little code, a little piece of code that converts a random number between 0 and 1 into sampling from this distribution. Generative models can tolerate missing values, right? We can model the probability of a missing feature value, right? And we'll see this specifically for naive Bayes, right? And descriptive models cannot model a tolerate missing value. And one of the, if we're, I don't know, here it doesn't quite make sense if we have one feature, but if we have multiple features and one of the features is missing, we can use the laws of probability to marginalize out that missing value. So in discriminative learning, if you don't observe one of the input feature values, you lose all of your guarantees, right? You have some, you did cross validation, you have this, you show that you should expect this level of training error. If you miss one, if you're missing one or two of your feature value input features, if it's an important feature, who knows what your performance is? You'd have to redo the whole process, ignoring that feature. I mean, it becomes this very tedious process, right? And if then you turn out to be missing some other feature value, then you have to redo that whole process again. Many people in the machine learning community find generative models more elegant, right? So they like specify a complete description of the universe that you're trying to model, right? I have mixed feelings about this viewpoint, but in some ways they tell a more complete story about the data, and this is very useful if you cannot decide what you want to do with this model a priori, right? If you want to learn a model that then you can query, right? Like you're working with like a domain expert, like a social scientist, and you're modeling, I don't know, Twitter data, and the social scientist asks, what, condition of this, what fraction of people like this? They ask all these queries, right? If you fit a good generative model over the whole data set, you can answer all those queries using Bayes' rule, right? At least subject to the accuracy of the model, right? So, the idea is that, pick a model first, right? Train the model first, and then pick what is the Y later, in some sense, right? Any of the input features could be a Y, right? We'll just train a model first and figure out how to sort of ask questions about the model later. Any questions on that? Okay. All right, so now we're going to talk about a specific model called Naivebayes. This is the simplest probabilistic generative model that sees use in practice and is, I think, a quite elegant model. So, we have a binary in this simple version. We have a binary y, so it's 0 or 1 or -1 or 1 or whatever, and we have a d-dimensional vector of x's, and each x is also binary in this simple case. So each x is 0 or 1 or whatever. You can think of this as, in the text case, you can think of this as whether a word appears or does not appear in a document, right? And then our goal is to learn a probability distribution p of x comma y, right? All right, so here's an example with two feature values, right? And a binary y. All the x's in this case are going to be binary, right? And in this case, again, it's completely unstructured. This is not naive Bayes. This is completely unstructured. But we learn a unique number per. We have a parameter for each unique entry in this table, right? Can anyone tell me what's wrong with this approach, especially as d gets large? Yes.
The number of parameters increases like exponentially.
Correct. The number of parameters scales exponentially. So for d equals 2, the number of parameters is quadratic in D. in the number of unique values. So so the base of the exponent is 2 and the exponent is d, right? If your x's have more than 2 values, if they're categorical features with like 3 or 4 or 5 values, then the base of the exponent gets larger. All right. So the model complexity is exponential with respect to length of x, excuse me, which is d. So this is what I mean by unstructured. When you're unstructured, you're basically just memorizing the training data, right? You have a single model parameter for every unique entry in the data that you're trying to model. If this was an image, right, a 256 by 256 image, then you'd have 256 feature values, right? Features, excuse me, 256 squared features, and that's just impossible to model in this unstructured way, right? So let's talk about naive Bayes, which does make a very, very strong structural assumption on the data, right? So naive Bayes posits the following generative model. It assumes that first you generate the true distribution. It makes the assumption that the true distribution that generates all the training data, right? First, it samples in y, and then conditioned on the y, it samples each of the x's independently. Condition independent, right? So you can express that. This is for those of you who haven't seen this before. This is called a graphical model diagram, right? So a lot of probabilistic models can be written in terms of graphical models. And what the graphical model tells you is it tells you the conditional dependence assumptions of the model. But in this particular case, this x, if you condition on the y, this x is independent. The probability of sampling, or whatever this x value is, its probability is completely independent of everything else in this model if you condition on the y, right? So that's what these arrows mean. And so now you can write that down in this form, right? So the joint distribution is modeled as P of y times P of x of d, x super d given y, right? Where this, because this guy, right, factorizes into this product because each feature value of x, each feature dimension, excuse me, is condition dependent given y. Okay, so why is naive Bayes so convenient? Well, it gives us a compact representation, right? So rather than having a number of features having a number of parameters in the model that scales exponentially with the feature dimension, it only scales linearly, right? Because the only thing we need to keep track of are these guys, and we have one of these per new feature dimension. So the complexity of the parameterization of this model is linear with respect to the number of feature dimensions. Each of these individual components is going to be easy to compute, and I'll go through some examples. And it's going to be easy to learn the parameters of these models, or estimate the model parameters of these models. And it's easy to sample, so if we want to draw new samples, it's easy to sample. And it's easy to deal with missing values. So all these are going to be true under this structural assumption. And we'll go through some examples of how that works. Here's a very simple example, right? So this is a probability table of P of x given y. So each row is a probability of P of x given y, right? Sorry, excuse me. Each cell is a P of x given y, right? So the complement is is the 1 minus this value, right? And then here's P of y, right? So imagine that we've estimated this model from data. These 6 numbers sort of summarize the entire model. These 6 parameters. already said that. Okay, so how do we make predictions, right? Remember that oftentimes the prediction we want to make is P of y given x, right? And so by Bayes' rule, it equals this, right? And then this guy, right, factorizes multiplicatively into each P of x a super D given y, right? And you know, because this guy this guy's conditioned on x, right? So we're only considering like y, the two values of y. You know, it's proportional to this guy because it doesn't really depend on P of x, right? And so because it's proportional to this guy, right? Then we just compute this value. We just compute this for y equals one value, y equals the other value, and then we just and then we could divide, we could normalize because we know that it has the sum to 1, and then we're done. And these are exactly the model components that we keep track of, right? We keep track of this guy as our parameterization of the model explicitly keeps track of this guy as a table and these guys as a table, right? And so all we have to do is just compute the numbers by multiplying this together for a probability table, normalize because there's two values of y, and then we're done. If there are more than two values of y, then we just compute this for all the values of y and then normalize and then we're done. So here's just an example, right? If we want to compute P of y now for some specific x, right? If we want to compute P of y equals 1 given an x, you know, we just apply Bayes' rule, and these were some of the numbers that we can compute. So these are sort of the product of all the possible x's. I just pre-computed that for simplicity, and we get a number that looks like this, right? Okay. Suppose here's a different one, right? Suppose we want to compute P of x equals to 1, P of the first feature value, given everything else. So we've observed the y in this case. We've observed every other feature of x, but we didn't observe the first feature dimension of x, right? Well, recall that condition on y, right? P of x1 is conditionally independent of everything else. So this is literally just a lookup in the probability table. Suppose we didn't observe y, right? Suppose we didn't actually observe y. We're missing that value. And now we want to compute P of x1, given the other x's, right? Then you simply just marginalize out. By the law of conditional probability, this is P of x, all of x, divided by the P of x of the second to the last features, right? The rest of the features. And this is equal to just marginalizing out, the P of y, right? And so these are all entries. These are all things that are explicit in our probability table. So we could all look up these numbers, and we just sum over all possible y. Oftentimes, it's convenient to represent these parameters in a matrix form. It's just more convenient, and in the homework assignment, that will be the case as well. Yeah. So, if this O matrix was representing these numbers, right, and then there's the P matrix, you can just look at an entry of this matrix multiply, matrix vector multiplication. This is going to, once you get a handle of thinking about these probability tables in a matrix form, coding it up would be way easier to debug than keeping track of all these superscripts and subscripts that I've seen some people do. Way more. It's also computationally faster because you're exploiting vector arithmetic in the processors, but it's also just a lot easier to debug. Right, so here's another case of missing values, right? Suppose we don't observe the second feature dimension, and we want to predict, again, recall there are two feature dimensions in this very simple example, and we want to predict the y given only observing the first feature dimension, right? And so again, here I'm writing out for a capital D, but in this example is only 2. So we can marginalize out, right, the other feature values, and so we can write out this guy as this guy, which is equal to this guy. For general D, this might look daunting because this sum, that the number of unique x feature values scales exponentially with capital D, right? So initially this might seem daunting, right? But this marginalizing out for general D might look like it takes exponential time. But it turns out that with the Naive-Bayes assumption, right? With the Naive-Bayes assumption, again, this is the definition of Naive-Bayes. This is what we care about. This is what we care about. We can write it out in this form, right? And because everything's condition independent, we can swap the product and the sum because each of these terms are independent of each other. We can swap the product and the sum. So now we're only summing over each individual entry of each feature dimension of x independently, rather than summing over the joint lattice of all possible x vectors. And now this takes linear time, right, rather than exponential time. And this is only possible because of the independence assumptions of Naive-Bayes. If you had an unstructured table, you'd have to actually sum over an exponential number of possibilities. Oh yeah, sorry. In the particular case of Naive-Bayes, it actually just completely marginalizes out. In other more complicated models, you'd have to actually do some summation. Yeah.
So in practice, do people really use Naive-Bayes as opposed to something like a Gaussian process? If you have like a good covariance kernel.
Yes. It depends. Yeah, people still use Naive-Bayes in practice. It's often a reasonable model to try. The problem with Gaussian processes is that their complexity is quadratic and scales quadratically rather than linearly. So there are often reasons to keep this simple, right? If you're doing rapid prototyping on some data set, you just want to get a quick feel for the model. Naive-Bayes and its generalizations, there are extensions of Naive-Bayes that are a little bit more make things more complicated, but yeah, Naive-Bayes and its generalizations are often much more compact. Yes?
What do we do with the probability of x to the 1 in the denominator? Going from the first line to the second line?
That,
Or third line, first line to the second line?
is there, let me see. That is P of y given x1. No, hold on. No. Sorry. This is the numerator. This is the numerator of this guy. Yeah, that's it. So this is equal to this, which it gets plugged into the numerator of this guy.
Sorry.
Yeah.
For the purpose of summary derivation, that's by definition you can go from the first to the last.
Okay, all right. You know what? This is a super simple model. Maybe I made it overly complicated. If you actually if you work this out yourself offline, I'm sure you can all convince yourself that these are very simple manipulations to make. We don't need to. Yeah. Okay. You could jump a number of these steps. I agree. Yeah. Here's a 3-variable case. Again, I don't expect you to look at you don't need to follow the details. You can follow it offline. This is just the intuition of 3-variable case, right? So let's jump up a level and compare this to logistic regression, right? Again, we can, just to recap, we can query any distribution, right? Training just requires counting. Naive Bayes is not optimized for classification accuracy. We're trying to maximize the joint probability of the XY pairs. Logistic regression, we can only query P of Y given X. The training requires an optimization procedure like gradient descent. And it's trained to minimize the negative log loss, the log loss of P of Y given X, excuse me, and cannot tolerate missing values. So so here's a study from a paper that I referenced before, and here's just a very detailed, broad set of comparisons, and Naive Bayes basically comes in last place on over half of the experiments that they did. So if your goal is explicitly to predict this type of Y with no missing values, you should not use Naive Bayes. So training, so again, we're going to maximize likelihood or minimize the negative log of the probability, also known as minimizing log loss under this model. And the P of X comma Y will have the Naive Bayes structural assumption, right? So the parameters of the Naive Bayes model factorize into learning the parameters of this table and learning the parameters of these tables. Again, is this counting? P of Y equals spam is just equal to the number of times that spam appears in the training set divided by the total number of training examples. So that's how you fill in that probability table. This probability table is equal to the number of times that Y equals spam and the first feature value equals 1 divided by the total number of times that Y equals spam in the training data. And you could derive it using a similar technique that we looked at in the beginning of the class. For regularization, people have pseudo counts, right? So these are just similar form as we saw before. Typically, it's just a uniform distribution. That's what people do. So Naive Bayes is a generative model, right? We can actually sample data points from this model, right? And in fact, most of the time when we sort of say this is a generating probability, we actually make it an implicit assumption that the true data generating distribution has the same structure, right? We often implicitly make that assumption. Now that, of course, can be a strong assumption, but that's sort of one that you need to make in order for everything to be somehow well justified. So we assume that we can sample data in the same way, right? So first you sample Y. So you have this hierarchical structure, you have this hierarchical dependency structure where everything is dependent on Y. So the first thing you do is you sample Y. So you draw a random variable, right? And in the case where Y is binary, right? If the random variable is less, it's either spam or not spam, and according to the value of this random variable, right? And the condition of having sampled this Y, then for each feature dimension, we sample another random variable independently for each feature dimension, and then we only look at the part of the probability table for that feature value conditioned on the Y that we just sampled. So this Y is fixed, and so we just sample a random number to sample whether or not this feature dimension should be set to 1 or 0 using a completely independent random variable. So the number of random variables we use here is d plus 1. And each one is supposed to be independent of each other. And for more complicated generative models with multiple levels of hierarchy, this can get pretty complicated. But this is just sort of the simplest hierarchical sampling scheme for basically this is one of the simplest probabilistic models, Naive Bayes. And typically when you have this graphical model structure, right, you sort of sample in topological order as defined by the graphical model. Right. So here's an example. So here's the probability tables that we've learned for this model, right? And so the first random number we sample is 0.5, so we set y equals the span, right? Then we sample for the first feature dimension, conditional y equals the span. We sample 0.1, so we set the first feature dimension to 1. Then for the, sorry, that should be 2. So we sample 0.9 and set the second feature value to 0. That's basically it. And of course, if you have capital D such feature dimensions, you would just repeat this process for each of the feature dimensions. Right, so the order is actually independent. So this whole process is independent of the order of the how you do this feature dimensions, because they're independent of each other. Just another example. Get a different set of random numbers, you get a different set of feature values, and a different y as well. Okay, so just to recap naive Bayes, it's a probabilistic generative model. It makes some pretty strong independence assumptions, or structural assumptions as we often call them, on the generating distribution. Recall what I refer to as the unstructured case basically boils down to memorizing everything, right? But that's typically the complexity that scales exponentially with this size of the problem you're trying to learn. By making these strong independence assumptions, we have a compact representation that's easy to train, easy to compute various forms of probability, so easy to query the model, as they call it in Bayesian machine learning. Querying the model means computing some sort of conditional or marginal probability. It is not the most accurate model for most standard supervised learning prediction tasks. Any questions? Yes?
Use a sort of generative model to feed into the boosting procedure, or is that generally considered bad form?
What do you mean by boosting?
I suppose just directly resampling the data could be used to generate new data and then use that to feed into the booster. Is that considered a bad idea?
Generate new data for boosting. That's probably a bad idea. I'm having a hard time articulating exactly why. This sounds really bad. You'd have to have a really, really high confidence that your generative model is really closely mimicking the true distribution. Right? If you're making like a very coarse query, like P of x, the third feature value of x, you're making these really coarse queries, this model gives you some insight. If you want to maximize prediction accuracy when you're already at 90%, you want to get to 93, you need a really, really, really accurate generative model.
Kind of interesting that when using a generative adversarial model, which is like one of the fancier ones that we'll probably talk about at some point, I found that on the CFAR10 data set, essentially like training the model on the training set to generate like new images did end up improving test accuracy.
Oh, it did?
Yeah.
Okay.
Yeah.
Yeah, if you had a really accurate model, you can. I would not recommend naive Bayes.
Well, at that point, why not just use your generative model to do the prediction if it's that accurate?
Right? So the answer for these really complicated models. Okay, I have a few answers. First of all, for these really complicated models, the sampling, the applying Bayes rule is non-trivial. Right? It actually sometimes it requires solving an optimization problem. Right? So like, sometimes it requires actually solving an optimization problem because there's the parameter. It's parameter in such a way that computing some of these probabilities requires solving an optimization problem. And so directly using these generative models for these type of predictions at runtime is typically inefficient. compared to just a feed for a neural net, let's say. Yeah. That's one. Two, and this is and the second point I'm going to make is not completely well understood. It's a topic of current research. For these really, really complicated generative models, right, and these really, really complicated large neural nets that's making, let's say, image classification, right, it's not 100% clear what value the generative model is providing. Is it providing hallucinated data to help regularize the supervised learning task? Because it's really easy to trick a neural net into. I don't know if you've seen, I think we went through some examples when Joe gave a lecture where you just modify a few pixels and it goes from predicting a caterpillar to like a truck, right? And so that is an instance of overfitting, right? In a way that's poorly understood. Because it's not just about a linear feature vector. That form of overfitting is, like from a mathematical perspective, is poorly understood. And so this sort of adversarial or generative modeling, you can think of it as a form of regularization, where it's generating more data on this like basically low-dimensional, some implicit low-dimensional manifold of images, right? That's basically what's happening. And so that will sort of constrain the supervised learning component to sort of focus more on data points that lie on that manifold. This point, again, is not well understood. It's a topic of current interest, but that's sort of one of the intuitions that people have. That's a great question. But Naivebayes don't do that. If the generative model is really, really bad, it's just not going to help at all. For Naivebayes, it's often the first thing people try to like make some coarse queries onto the data sets. Like when you do prototyping, right? You start with something really simple, just as a proof of concept, and then you move on to heavier duty stuff. And Naivebayes is often used these days as step one. You can invent your own model. I just created a model where we're predicting two y's, right? And I just posited it that y1 is dependent on y2. The last feature value is dependent on y2. The other feature value is only dependent on y1. I believe that's. Yes. This is not a decision tree. Because in a decision tree, we predict a single y at the end. It does have a topological order to it, but it's not a decision tree. Because at the end of the day, we predict everything. Okay, I'm going to conclude this lecture by just going over a very high-level survey of a few other probabilistic models. So there's Gaussian Naivebayes, so the question about what happens if the variables are continuous rather than discrete. And if you make some assumptions like that the generative distributions of the x's conditioned on the y's is Gaussian distributed, or we want to learn the mean, and if let's say we know the covariance of us, we could also learn the variance or standard deviation, or I guess that should be variance. Then you could learn a continuous distribution. You have the same independent structure, so how you model the Gaussian distribution for each feature value is independent of all the other feature values, conditioned on knowing the y. Right? You have the same independent assumptions. So you don't have this really complicated interactions between the means of the different variables. Hidden Markov models, this will be the focus of the next lecture, next two. It'll also be the bulk of the homework. It's a generative model over sequences. And so you can think of each token or term in this sequence as a naive Bayes model, right? So if you ignore the fact that there's a sequence, each individual thing, in the token in the sequence is a naive Bayes. And then, but there's also a sequential dependency in the y's. Right? And so we'll talk more about this in the next lecture. But this is a generative model over sequences, such as sequences of words. Gaussian mixture model, so this is a probabilistic version of clustering, right? So imagine that there are k Gaussian distributions, and you know, we sample a distribution. You know, we sample. You know, we first pick one of the k Gaussian distributions, and then we sample from the Gaussian distribution to sample our data points. So each data point is sampled first by picking one of the k Gaussian distributions, and then conditioned on having picked that cluster membership, basically, each of which is a probabilistic cluster, has a probabilistic generated distribution of a Gaussian. Then we sort of sample from that Gaussian. Right? It's in 1D with 3 Gaussians. It looks something like this, right? And if you think about k-means clustering, right? If we assume that there are sort of, let's say, 3 clusters in k-means, and the distribution of the data for each cluster is sort of Gaussian distributed around some center, which is sort of what it looked like in the pictorial example I gave a couple weeks ago, then this type of model can actually generate a data set that looks like that. Right? Topic models. So this is called latent Dirichlet allocation. It's a version of what's called a topic model. And so these are pretty complicated, but again, it has a bunch of hierarchies here. So before, when we looked at Naivebayes, there was just basically this guy, right? And now there's multiple levels of sampling. And so this n just basically means that there's n, n words in a document, so capital N words in a document. And so we sample a random variable for each word. So for each word entry, we sample what word it is. It depends on some topics. Each topic has a word distribution, and there are capital M documents. So capital M is the number of documents. There's n words per document. You have this big hierarchical sampling procedure to generate a collection of documents. So, you know, for whenever you define these sort of generative models, you know, you make a number of assumptions, right? So here we're positing that documents are represented as a mixture of topics, and topics are represented as a mixture of words. And we want to learn, and the parameters of this model is the document mixture, the topic mixture of the document, and the word mixture of the topics. And so here's some visualizations of LDA analysis of Sarah Palin's emails. This was the top result when I searched for LDA example. I think last year I did it, or 2 years ago. This is literally the top result, so there's no bias here. I would have taken whatever was the top result, assuming it was appropriate, family appropriate. So here's just the top words of each topic that was learned. So you infer this model. So you train this generative model to maximize likelihood of the words in all Sarah Palin's emails, where each email is a separate document, and then that is sampled independently. So you maximize the likelihood of that, right? And then you fit your model parameters, and then you can actually visualize your model parameters. So for each of your topics, you can look at what are the words that are most prominent in that topic, and these are the words. The headers, the bolded headers are provided by the person who did this study. So that person actually assigned those headers to each topic via inspection, visual inspection of the topics. So here is an analysis of a document, right? So you can say, you know, this particular email, the LDA inferred that this particular email is about 2 topics, or at least 2 topics, one about the presidential campaign and one about wildlife, and then you could even infer which words belong to which topic, because each document is a mixture of topics. Each topic is a mixture of words, so you can estimate all these for every data point, for every example document in the training set. Moving on from text, we have images, right? So you can generate, for example, using various deep learning techniques, you can generate, for example, this is your reference image, this is the image style, and using statistics of the local patch information of this image, of this stylistic image, we can transfer the styles onto this image, so we preserve the content while transferring the style. So here's with a few different images, a few different stylistic images. We can, I'll let you look at it for a little while. By the way, they have demos of this at every machine learning conference now. It runs in real time on the NVIDIA GPU nowadays. So like you could like film someone, you could like, and then it gets stored as stylistically transferred. Yeah.
Styles are the prior?
Yeah. So here the prior is on. So here there's a distribution over basically local like patches of image, like local patches, and it tries to sort of find the best possible transfer. Yeah. You could generate completely new synthetic images from scratch, right? And so here's two examples. So here we're generating images of telescope imagery, right? These are completely synthetic images. They're generated just from random bits. So you feed in random numbers, you output these, right? Volcanoes and mountains. So these are, of course, much more complicated generative models, but all like the basic principles that I outlined in this lecture applies. This is a project that we recently worked on where we're actually modeling trajectories of NBA players. If you are interested but not too judgmental, we have a prototype interactive demo here. It's still a work in progress. It's not the most polished interactive demo, but it works, and we hope to make it better in the coming months. You can try it out, and if you have any feedback, please send me an email. But here's an example. So one of these was generated by, so we trained on trajectories of NBA games, and we want to simulate new trajectories of NBA games. One of these is a generative model that we designed. One of these is a baseline. So this one's the baseline. The players go out of bounds a lot. And here's a model that we generated. And here, you actually have to build a generative model that models coordination between the 5 players, right? And so you have to figure out where to model this complex, potentially exponential dependency between the players, and where we can sort of make independent assumptions so we can sample the rest of the players' behavior independently. And so this is a project that we just concluded. And here's just an example where if you sort of condition at the beginning of this trajectory, and you roll out and generate multiple samples repeatedly, it actually generates different trajectories. It's not deterministic. Right? These are all this somehow reflects the distribution of actual behavior that a player, starting from that initial condition, might end up behaving. So there's no single right answer. You can sample from this distribution multiple ways. Okay. Okay. So just to conclude, generative probabilistic models, their goal is to learn a probability distribution over the whole data set, over the whole example, right? Not just y given x, right? And in such a way that can quantify various forms of uncertainty in probabilities. Therefore, you can tell missing values. These models represent some sort of summary of the data, right? And you fit the parameters of the model to the data to maximize likelihood. That's how the vast majority of these models are learned. You can use these models for inspection, right? If you want to do some quick rapid prototyping to understand what the data is telling you. You can use the model for generation. Sometimes generation is itself a task now, increasingly so in the machine learning community, like generating new images, generating basketball gameplay, generating music, generating, actually I have a collaboration with a Hollywood tech company on generating movie scripts. These models are not trained to predict accuracy in the supervised learning sense, right? So if that is your goal, you should not be using these types of models. but they offer a lot more flexibility if you're interested in tasks beyond that. Any questions? Yes?
So you said these things are non-deterministic, right? So what's the impact if you back a bunch of generative models together to make a prediction? You just get the average, or like would it be then deterministic?
Like for a single y, like p of y given x?
Yeah.
Well, I don't know that you'll do much better because bagging requires, well, you might, for some generative models, you might improve performance by a little bit, but you're not going to beat a random forest or an ensemble of deep neural nets. It's just not going to happen. An ensemble of supervised learning deep neural nets. It's just not going to happen. Yes?
How do you decide what to work on? Like, you gave us examples of basketball and then the face thing with the words. Like.
Me personally?
Yeah.
Okay, so beyond the scope of the class, and if you're interested, I'm teaching CS159 Advanced Topics in Machine Learning in the spring term, which is more of a research-oriented class. All the PhD students should be taking that, by the way. But undergrads, of course, are also welcome as well. And it's the choice of what research project to work on is a very personal decision. For me personally, I love working on really cool applications that require new machine learning methodologies and theory. So, if it has to check all the boxes of it's a really cool application, very few people are working on it. If you just apply existing methods onto this application, you either have to hack it a lot or engineer it a lot, or it doesn't work very well. And I think I have a reasonable insight into how to start developing a new class of algorithms or theories that can better characterize this application so that even a very simple approach can give you huge gains. Yeah, so like for example, the generative model basketball gameplays didn't exist before. And no one was able to really do it before. And then again, if you're interested, please, come take 159. It's a much easier class than this one. It's paper reading, and I'll talk about it by the end. And at the very one of the last lectures, I'll talk about it a little bit more. It's paper reading and a final project. No homeworks, no exams. Okay, I hope I don't get too much enrollment now, but anyways, just to summarize, let's close out. So starting next lecture, we'll look at hidden Markov models in depth. We'll require dynamic programming, which if you don't know, we'll kind of get into that in very painful detail in the next 2 lectures. And that's it.